All right, we are live. Let's get started. So, hi and welcome everyone. I hope you all are doing great. Thank you so very much for joining us and spending your Saturday evening with us. I'm pretty sure it's gonna be a good learning experience for you. My name is Rashmi and I head the developers community here at Recro. And I am super thrilled to host this webinar today. Today we are gonna cover high level design and we will learn the same by Akshay has an amazing presentation prepared for you, and we'll learn how companies like Uber, Zepto, Ola does demand forecasting and have dynamic pricing using, of course, a high level design, right? That's why we all are here for. So awesome, glad to have you here. Please let us know in the chat where you guys are joining us from. I would love to know that as well. And I request you all to please kind of make this session very engaging and very very interactive as well. So yeah, let us know in the chat where you are joining us from. All right. Now, quickly introducing our guest speaker for today, we have Mr. Akshay with us, um, and he's a IIT Bhubaneswar graduate, and he has worked with brands like Gojek and Dunzo. He also has experience working for fintech, building payments, management based product, etc. Not only that, Akshay also has an experience with entrepreneurship and co-founded a knowledge management company. Akshay, welcome on board. Thank you so much for taking out the time and for joining us today. Yeah, over to you.
Sure. Just an introduction to me. My name is Akshay. I'm a staff engineer at SQA. Uh, uh, what I do as my hobby is basically I code a lot, and I love solving complex problems and book reading generally. Yeah, that's pretty much it about me. And today, I think you'll be telling the introduction, right, about the topic.
So Akshay, if you could, so I'll
Sure,
quickly
sure, sure.
I'll quickly take people who are listening to us live. I'll quickly
Hmm.
tell them few important notes,
Sure, sure,
and once that is being done, then the stage is all yours, and then you can
sure, sure,
nicely explain about
sure,
the
sure,
topic. Yeah. So
sure, sure.
folks, thank you so much once again for joining us. Before we start this webinar, there's few things that I wanted to share with you. First, this is gonna be a very important session for you and for your learning, so please have a lot of questions. I think we'll be having 40 to 45 minutes conversation on the topic, and then last 15 to 20 minutes will be for Q&A. So have a lot of questions ready. Do take screenshots of this session so that you can also refer to the same after the session as well. So feel free to do that as well, and we would love to see those screenshots and some of your learnings, whatever the key highlights that you take away from today's session on LinkedIn. Do that. Tag Akshay as well on LinkedIn, tag Rebase by Recro as well on LinkedIn, and we'll love to see your post. Second thing is, this webinar is brought to you by Rebase by Recro, which is a developers community that I, along with my team member Canada, we are building. We are around 2,500. We have 2,500 developers on the Discord server. So if you are someone who is looking for a community to learn from, want to connect with like-minded people, network with them, finding job opportunities, feel free to be a part of our server. It is free to join, and I'm pretty sure it's going to be a good learning experience for you as well. So that's pretty much it. And again, welcome to the session. Have a lot of questions. We will take it up at the end. Akshay, I'm all set with the introduction. Over to you.
Sure, sure. Can you just allow me to share screen?
Yes.
Yeah, sure.
Okay, it's done.
Uh, oh, I need to allow my screen sharing. I'll just rejoin again. I allowed screen sharing. I'll just rejoin again.
Sure. In the meantime, folks, I would love to hear from you where you are joining us. How many of you are joining us from Bangalore? Also, just a quick announcement again. While we will be doing the Q&A at the end, if you would like to be on the screen, I can also invite you on the screen to ask questions. Yeah.
Cool. I think, can you guys see my screen?
Yes.
Yeah. Is this visible?
Yeah, Akshay, it's visible.
Cool. I'll start off. I think today we're going to cover mastering high level design. Essentially, I'll be telling you what is system design, and I'll tell you what are general components of high level design. Then I tell you how to structure your thoughts on better design, and then finally the main part is where you implement a problem statement, which is implementing a dynamic pricing for a ride hailing app. And this while you implement this, you will use your learnings from the first three steps. Cool. So what is HLD? What is high level design? High level design is nothing but a blueprint to build a system. What is a system? System is just an interaction between components, which will effectively produce a feature or a product. What is a feature? Is a set of requirements. So essentially, when given a set of requirements, you would have to provide a blueprint for those requirements in order to build it very efficiently. So what would building a blueprint give you is, without a blueprint, a system may not function as intended. This can lead to performance issues and having a bad system and an experience for customer. So that's what system design means. Moving on, let's start with the general component system. This is so that we'll be using all these components. So just to give a very brief level view on this. The first one, generally a system would look like this, where in which your web servers are there. Web servers will call a load balancer, and load balancer will hit your servers that is there. So your mobile app calls load balancer. Load balancer hits your web servers. Web server essentially stores its data into a database or a cache, and also it publishes to a message queue for asynchronous processing. And there'll be workers consuming from message queue. So let's go through one by one a brief idea of what web server is. Web server is nothing but all the code you write for hosting your program, or what it's supposed to do, what your logic is supposed to do. That means stores, processes, and delivers data to the web. Next is load balancer. So essentially, a single web server is just, imagine a computer being there as a web server. Now your computer cannot handle, let's say, 1 million requests per second. You will need to distribute it among multiple web servers. That's a job of a load balancer. Load balancer distributes these data into multiple web servers or nodes based on any logic. Like, for example, one logic could be round robin. We'll go through all that logic coming in the coming sessions. The next one is, what is a database? As you all know, database is used to persist data. There are different kinds of classification for database. Here I'll explain about basically three types. One is based on data model. Data modeling of database, there are multiple types. One is hierarchical, there is a legacy one. Now there's relational, NoSQL, there's also new SQL, graph, and columnar. These are some of the data models, how you classify database as. Then there's based on replication. Based on replication in the sense, database doesn't store, like, let's say one node of a database is there, it might not store the data in that only. It might replicate to other nodes to provide fallback mechanism to have higher availability and stuff like that. So you have master slave replication, where in which you have a master and the slave replicates from the master and has almost the same data or exactly the same data at some point. And there's also master, where there are two masters, and this provides really high availability. An example of master slave is nothing but Postgres. You can have master slave configuration in Postgres. Example of master is like a CouchDB. The next one is based on data distribution. So you might have a single node database. You can have multi-node databases, and essentially most of the database support multi-node at the moment. Then there's something called cache. Essentially, web servers store its data in disk, and as you all know, it's hard. It's more time consuming to consume data from disk rather than memory. By memory, I mean RAM. Now, what does a cache do? Cache stores most of its data in memory and using your data structures like a hash map, heap, whatnot. So cache stores like that. So which means there's a faster memory access to this. So the essentially performance of the cache will be much better than the performance of a database. But what cache cannot do is persist data. Even if it persists data, it has low guarantees on it. It might flush data into some interval, so data loss might occur and stuff like that. There are two types of cache: single node and cluster based. Then there's CDN. What is essentially the CDN? CDN emerged as a way to store static files initially in the HTML era, where HTML static files used to be stored in CDN, and that used to be consumed for faster delivery to the customer. Then there's message queue and workers. So there are some processes that needs to be async in nature. Example, let's say sending email. Sending email is not very straightforward. You might have to communicate with the SMTP server and sending a huge amount of bulk of a data through network, which might take a lot of time. So things, and but these need not block the customer. Let's say in our case also for pricing, you get the price for getting the price of a customer, or let's say you book a cab through Uber. Now, once you book a cab, you don't need the email to come directly like you have booked a cab. You might it's fine if it takes some time, and so these kind of things you can move to an asynchronous processing. That's an example of how asynchronous processing, and there are workers consuming from these message queues, which will enable you to process whatever logic you want to run on these messages. Cool. Moving on. Uh, Now, how do you design? Let's say any problem that is given to you for high level design. Essentially, you start off with requirement, because you think as a customer and ask, or as an engineer who doesn't know anything about the problem statement, and you ask basic questions to understand the whole domain of the product, and also to gather whatever requirements are needed to build the feature. So essentially, requirement gathering would mean asking the right questions and making assumptions. An example is, let's say I tell you to build say like Uber or something. So the first thing we would ask is what is the product exactly doing? Can it support, let's say, multiple rides? Can it support let's say should we send email immediately once, let's say, you book a ride, or should we deduct money immediately after you book a ride? Things like this. These are all requirement gathering where you understand the product. What also you should gather from that is the scale at which you will be building the system. So the scale to a product. Let's say you're talking to a product manager when you're building a product. You'll be like, what are the daily active users you already have? This what would aim of these questions are to understand the domain and to make sure you have enough knowledge to build your functional and non-functional requirements. So now let's go to functional requirements. That will make more sense now. So what is functional requirements? Essentially, let's say you're building a login page. Your functional requirements would be user should be able to log in, and let's say an admin should be able to delete or blacklist you from the web page. These are functional resources. What as a system, what the product wants you to perform, or the aim for getting this is to exactly know what all features have you built. So after your system design is done, or your final diagram is done, or the blueprint is done, you ask, okay, you check whether all this requirement is being satisfied. Then there's some more requirement which is not directly present when you requirement gather, which is like non-functional requirements. This, as an engineer, you have to ensure that your system is performant, reliable, reusable, secure, and scalable. So now, what example of such things would be like your system should perform at very low latency, or your system should perform, you should have like 99.59 availability, things like that. And it's not like every system should have low latency, right? It could be that low latency might not be a must, and to acquire, like, to have low latency, there are some trade-offs that you have to make, and those trade-offs need not be there, things like that. So what your aim in this non-functional requirement is to understand the technical implications, and we need to keep in mind when you're building the system. Cool. The fourth thing is estimation. I think one of the most important thing here. You ask your requirement gathering, you got your product base, how many daily active users are there, or how many requests is going to come. So from there, you understand some things, and those some things are these. Requests per second is one of them. So how many requests per second will your system be serving? Query per second is another. Let's say how many query per second will be hitting your database. What are the general access patterns that your database needs to do? So this will help you decide your components. So and not just decide a component, and how the flow will also be. So let's say if you are going to make some cryptographic hash function or something, a new requirement is to make, you will have a very high CPU intensive process. And it might not, let's say if it doesn't work in a single node, you might need to have multiple nodes, things like that. So it's a very and it depends. This estimation depends on your product you're going to build. And then what you do, but while you're doing these four steps, you will have your proposed design in your mind. So when you're building these steps, you need to build up a small system components that you'll be talking to the domain at least, and then figure out. And once you build that basic domain, you ask questions to yourself like, what is the issue with this, and then you continuously iterate on it. So let's go to the problem statement. Before that, if you have any questions on chat, you can ask regarding till the problem statement, because from now we'll be going full-fledged on how to solve this problem using these approaches. Cool. If there's no question, then I'll start. So what are the problems you're trying to solve now? As a ride-hailing company, I would like you to implement a dynamic pricing system which would change price based on demand and supply. This is what, let's say, a product manager gives us the statement, or an interviewer in some cases gives us. What would you do? So an example is a customer makes a request to travel from home to a shopping mall. our system should return a price based on demand and supply. In this case, our system returns 100 rupees. A simple statement. But there are a lot of things that are missing here we don't understand. Let's go one by one to them. So first one is requirement gathering. First thing is understand the domain. So what do you understand? How do you what all like when you see this question? Some of the first question, some of the first thing that comes, there's some word called demand and supply, which is not quantified. As an engineer, you would like to quantify these values. So yeah. So first thing you ask is what is the demand? Because you need to quantify demand and you need to see if you and the product manager are on the same page. So a demand, he says, is nothing but a number of pricing requests made by a customer in a city. Okay, so you mean to say if I make a request, I am a demand for the company. Now, but the problem is we don't have a time bound for this. When is the demand calculated for? So we ask like, what is the time for demand? Let's say 5 minutes. So now we have an idea that okay, what demand is nothing but the number of pricing requests that is made over the last 5 minutes in a given city. Simple. So now next question obviously would be what is the supply? Supply is the number of drivers available in a city, and same thing calculated over 5 minutes. So you have demand. Demand is the number of customers making the request for the last 5 minutes. Supply is number of drivers available for the last 5 minutes. Now, something else that you can ask is what are the factors that the price can depend on? Because just by demand and supply, you can't give a price. You need to give a price based on some distance, something. So that's when the product manager says, yeah, it's from distance from point A to B. So now you know the price depends on your distance from point A to B, the demand and the supply. The next question is how do you decide what price to offer per kilometer if it's distance? So the product manager says there needs to be interface to configure this, and the system should take the data. So there is some interface, some admin guy would be configuring this value, and a system will use that value. Now what as an engineer now we can think is there are two domains. One is distance-based price, one is demand-supply-based price. So those are two things we can confirm, and we can confirm with the product manager or the interviewer. Now, what more? Like, are there more components to pricing? You ask them. They say rain is one component, but we won't be discussing that in this slide. The next thing is how do you quantify price based on demand and supply? Let's say there is 5 demand. Let's say there is 5 drivers available and there is 5 requests coming. So he says you can think of it as a factor to multiply your price per kilometer. So you have price per kilometer, you have demand supply, you multiply some factor that demand supply gives, that is your final price. That is how we are going to model system as well. Now, some of the other questions are, can we assume one type of ride exists? Yeah, sure, you can. And one major thing is, do we need to build, because if you see demand and supply, it is not just used for pricing. In a company like Uber and all, it will be heavily used for analytics and figuring out right areas where to put more drivers in and stuff. So things like that. So this system can be used for multiple other reasons as well. So we need to think of it as building the system in a scalable manner. Now, okay, what do we infer from this? We need to build a pricing engine that would have two components. One is static pricing and one is dynamic pricing. Static pricing is based on distance per kilometer. Dynamic pricing is based on demand supply. Cool. Now, how do you quantify dynamic pricing? Dynamic pricing is just a single float value which you have to multiply static pricing with. So as you said, final price that we show equal to price per kilometer, which is static, plus a function of demand and supply into static price. So now, and to update this static price configurations, we have an admin API, and admin can call this API. Now, the next set of questions is to understand the scale. So to understand the scale, you see how many daily daily active users are present, which is basically 100 million. Let's say that's a very high amount of users. And there's how many drivers are registered in this app. It's 4 million. So maximum 4 million drivers can be there in your system. And how many requests does an average user make per day? Let's assume 4. Cool. Now we understand it's a very high scale app. We need to make careful considerations about latency and concurrency. Sorry. So I think slides are gone. Just open that up back again. Cool. Sorry for that. Can you see my screen?
Yeah, Akshay.
Sure. Sorry for that. Yeah, cool. Cool. Now let's go to the first problem, which is functional requirement. Now, how do you figure out your functional requirement for this system. A simple, you have to build a static price, you have to build a dynamic price, and you have to build an admin API. It is as simple as this. But there is some other requirements also coming in, which is non-functional requirements. This has to be low latency system because, as you know, customer is going to say book from A to B. He has to immediately get the price. Otherwise, there'll be bad customer experience, and he'll probably go to another app. And we need to consider availability as P0 because we had asked the question on here. So let's say if the dynamic system goes down, should we still show the price? Yes, showing price is of utmost importance is what was the requirement given to us, which is why we need to build a system which is highly available. And obviously with the scale given, it has to be highly scalable and concurrent. And some of the other thing that we can get from this is because demand and supply is not just used for pricing, we can build it as a generic system. Cool. Now moving on to the estimation. Let's start with a very basic estimation on from the scale we got initially. There are 100 million daily active users. An average person makes 4 trips a day, which means the RPM we are talking about is 100 million into 4 by total minutes in a day, which is 280,000 RPM. And let's say during rain and stuff, it might peak up. So we're just thinking a scale of 3x, a peak scale of 3x, which is around 840,000 RPM. And this is a high scale. That is Virat. So 840,000 requests will be coming in per minute. Cool. Now, as we said, now we understand the domain. Before we start building our components, let's have majorly two components in our system. One is the static price, one is the dynamic price. And we'll model dynamic price based on demand, supply, and in this case, rain if you have time. Then you'll multiply the static price with the dynamic price to get the final price. Cool. Before we move on, any questions you have on the problem statement itself or the requirements that we got?
Akshay, there is one question that is being asked by Aman over LinkedIn, and the question is how to decide how deep we need to go while thinking.
Oh, cool. I think we don't need to go deep at all at first. Rather, you would try to build a basic component. First, you need to first understand your domain. That is the primary importance of your requirement gathering. First, you understand your domain, you build basic components, and we will go deep one by one when we explain about each components. So let's say as simple as we have in this case, you have a static price, you have a dynamic price. I have not thought about anything else, not thought about data modeling, not thought about how would you communicate with each other, things like that. Over time, I'll be showing from first principles, how do you think and go deep for each component? You have just built a basic domain for your problem statement at the moment. And now I'll show you through first principles, how do you tackle this one by one and go deep internally.
Got it. Aman, hope you got the answer. Yeah, let's continue.
Cool. Cool. Now let's go to the data model. For a static price, so first thing we need is we know that there should be a configuration. And what all do we require for the configuration is simply leave the ID part and all. Let's say price per kilometer we require. We require the city ID, country ID, and the valid from and valid to. Valid from, valid to means till from when to when is this configuration valid. So this, if you do a higher estimation around this, it will be around 70 bytes with some buffer. And how will a request look like? The customer will send its from lat long and to lat long. Latitude, longitude, I hope you all know that. So it's just a way to identify where you are from. And now you have from lat long to lat long. He sends a request. We have to return back an API response saying this is the static price. The dynamic multiplier is 3. The final price is 300. Cool. Now moving on to how will you fetch the distance? So now in the request we only got lat long. So from lat long to lat long, how will you fetch the distance? Simple. For now, if you start building a Google Maps or a distance server, it will take time. That's why I'm just keeping this a black box for now. So we have a pricing service. We have a request that comes API gateways, something where your TLS exchange happens. It might act as a BFF. It is like an entry point to your whole network in your whole your company network. Let's say. So now once your request enters through this, it goes to your pricing service, which you're going to build. And pricing service should call a distance service to get the first how much distance it is there. Cool. Now once you get your distance, you need to multiply with the configuration you got. But there are some issues here. In this basic diagram I just made a pricing service called distance service. In this basic diagram, what are the issues with this? Here, pricing service is just a single node. So there's like 840,000 RPM coming in, which essentially means this single node won't be able to serve it. If you simply try hitting this in your own laptop, 840,000 requests on price, like any API, you would see your memory and CPU spike and your server crashing. Now, how would you solve this? You would solve this simply by having multiple instances of pricing service nodes. By nodes, I mean just a isolated memory or a CPU space, or it could be a single whole VM itself. Now you need to have multiple nodes of pricing service. Now, who decides if a request comes, should we send it to which pricing service or not? Does the API gateway decide? No, because that would be too much logic for it to handle. And obviously, you need to put a load balance, what's called a load balancer in front of it. Now, load balancer can balance your load, but there should be some algorithm in which it balances your load. Generally, preferred one is through round robin. It goes one way one. But in this case, also we can think of using least active connections, which means let's say load balancer makes to node one it makes 5 connections, to node two it makes 10 connections, and we know that node two is now going to be more on load. So we tell okay, make more requests to node one instead of node two, things like that. And now, obviously, because we're calling third-party distance service, you would be need to add circuit breakers and rate limiters, which is more of an LLD kind of a thing. So moving on, now we know that okay, there's an API gateway, there's a load balancer, you have multiple deployments of pricing service, and it calls distance service. Now, what you need to do is build a configuration store. So configuration store is nothing but what we said here. To store all this data, we need some place. So we need our pricing service will query for the data, hit distance service, multiply the values, price per kilometer into your configuration store value and return back. And your admin will be the one updating this configuration store through some API and through some role-based access, which I'm not going into right now. Now you're going to hit your configuration store. Now let's see what database should we choose for configuration store. That is one of the most important things you need to choose as a system. Because the language and all will already be pre-decided, or if you want some new language for the pricing service to be written, you will have to know it. But generally, it's preferred you follow org wide. If your company must already be implementing some language, it is good to follow this unless you have strict requirements on a language also, like very low high performing system you want to make and stuff like that, which is not the case for us. So here you have a configuration store, and now let's do some max here. You have 820,000 RPM coming in, and let's say for the admin, let's make there are 50 countries. This is an assumption you have to clarify, but let's assume that there are 50 countries and the admin API hits 2 times per day to update the configuration for 50 countries, which means there'll be 100 requests coming in for updating the configuration. And for our system, 820,000 RPM is there. What does 820,000 RPM do? It reads your data from configuration store. So there is 820,000 read queries per minute, and your update queries is a write query. So your writes are happening at a rate of 100 requests per day, which is very low. From this, what do you understand? It's a very read-heavy system and a very small write-heavy system. What do you think of what database to choose? When it's a read-heavy system, generally you prefer to offload your read and writes, and your writes need not be very, your writes are like 100 writes per second and 100 writes per day, which means even if one write took around 1 second also, it's fine for us because that low RPM we are getting. So now, so you're right. Let's say we will have a write system, but we will offload all the reads to a slave. So now you have a master slave architecture here coming in where you have multiple slaves, and your write queries can replicate it to all the slaves synchronously also because the given number of requests is very low. So you have a master slave configuration of a configuration store, and you have multiple slaves, and all your read queries that pricing request hits will go to the slave, and your admin queries will go to the master. Now coming to how much, whether it should be a single node. You must hear this word, right? Single node, multiple nodes. Do we distribute data, or is it fine or not? How do you do that now? Now you have, let's do some other calculation as well. From this, we assume that there are 70 bytes of data. We got that from the previous calculation on what you're going to store. 70 bytes of data per row, and now the app is live in 50 countries. So now and do 100 requests per day for the configuration for admin, as I said, which will account to around 10.5 MB of data to be stored. With the index and auxiliary tables, you will have around double the value. Let's assume worst case, which is 21 MB. So to store 21 MB, you can even store in memory. You don't need a database, but because we need to persist this for future use as well, you would need a database, and 21 MB can be easily stored in a single node, and we can have archival for 30 days. If you want more, it should be fine. So now the amount, even this amount of data can be stored. Like the database would use buffer memory and service data. It will be that far. Buffer memory is like a cache in the database itself where it stores in memory and then returns back the response from in memory itself for the most common queries. So now what database to use? You still know that it's a master slave architecture. It's a single node. Now what database to use? Columnar, as I said, is not a good use case of this because we need to fetch a single row for a single pricing request. You don't need to select all the columns, data select star and stuff like that. And now the next option is NoSQL or non-relational or relational. Frankly, for this use case, both would work. It would mostly be a choice like what your current company has expertise. It is there. How is the setup of, let's say, Postgres versus Mongo in your company, things like that. And both would ideally work because as it supports master slave, and if it supports read query and getting from a row, it should be very easy choice, and you can go with any one of them. Both would work. If for in this case, and because Postgres also supports JSON schema, to make it more scalable, you can have JSON schema as well. So if for this case, I would go with Postgres. Let's assume our company is more hands-on with Postgres, and we have proper automation deployment and monitoring on Postgres. So and with multi-slave, and there's a hot failover in case anything happens with one synchronous replication. Cool. Now moving on, there's the next question. Sorry, next part is now we have built a static pricing system ideally, but now we would also like the consumers to know. Let's say there will be other people who would want this data, this estimate data to like propagate through. So how will who are the consumers for this? So let's assume one consumer could be a demand and supply system, because our pricing request is a variable for calculating the demand. So now one consumer could be that. Second consumer could be an analytics engine, where you have to do where your data lake is getting this data, and you will have to do analytics on top of this. Third thing could be, let's say, some other analytics or some voucher system wherein which we know that customer is making so many requests, we have to apply voucher to him. Things like that. So there are a lot of consumers who would want this data, definitely. So the final price returned. So how will you notify these consumers? There are two approaches. One is you store your data in a data store, estimate store, and now your consumers can query through API and it fetches the data. Second option is you push through Kafka, you push through a queuing system, where your consumers now can consume from queue. What would you choose in these two systems? So don't know what's happening with this. Cool. Now, what would you choose between these two systems? Let's go. The answer always it depends, because it depends on how big your in this case our company is really big, but let's say a company is small and stuff, you would still go with the second approach, which is much easier to implement. The second approach is just exposing an API to consumers, but what you build there is a very coupled system. Your consumers are directly coupled to your system because now they'll have to query through an API to your system. But it's more of me telling, let's say I put a price and I tell all of you one by one that if you want the price, you come to me and tell, like, Akshay, what is the price? What is the price? It is that is what a synchronous system you're building. But if it's an asynchronous system, what you tell is, I have built a price, I just put a post, and anyone can read and do whatever with it. That's where the difference between this asynchronous and synchronous system comes in. What would you choose here? It's better to both asynchronous because you don't need the coupling over here. And let's say if one consumer suddenly puts in high throughput load and stuff, you will have to support that. And now supporting that means other consumers might get affected. That is what this coupling brings in. There are ways to handle that as well, but that will just mean more effort and work. So, and you wouldn't want to work in your system and some other system wants to change. So now that's why database approach would be taking a lot of load from consumers. You would prefer a queuing approach. Now, when you do a queue, what type of queue would you want to use? You would want to use a queue because what kind of queue? So here I would prefer something like Kafka, RabbitMQ, whatever it is. But the major point here is you would want, and we'll come to that what kind of queue we'll use in a later slide to discuss more on how do you choose this. And you would choose a managed queue solution, or you will host your own queue solution and support this high throughput. We'll be going with the publisher subscriber approach here. Cool. Now moving on. Yeah. Now what queue will be using for this? Let's do some calculation now. As I said, the total amount of data that we're publishing will be around. You can see the slide, but it will be around 150 bytes. So now, given we'll be publishing 150 bytes or 300 bytes, let's assume double of it also. This is a very ballpark figure. There'll be 840,000 RPM hitting our thing. So we'll be publishing around 126 MB of data every single minute. And normally, if you see a napkin estimation and stuff, you can see that a single network transfer of a single of 1 MB data would take around 50 microseconds over a very good network. Let's say you're in cloud and you have Jupyter network and stuff. Yeah, you'll have a very high speed network. This would take 50 milliseconds, so 50 microseconds. Now, for all this requests to pass through in a single queue, it would take around 6 ms, which is still okay for us. But can we improve this? Yes, we can have multiple queues there, and you can split this data around multiple queues. Which means, let's say using Kafka, let's say Kafka gives you partitions. Let's say we split this data around 10 partitions, you would have around 600 microsecond latency for this heavy amount of data. And so now what queue would be choosing? Frankly, all this most of the distributed queues support this kind of mostly support this kind of approaches, or you can also have this kind of throughput and stuff. But here I would say managing a queue in an org is another task altogether, and you need to have a separate team unless you're using a managed service. You need to have separate team and maintain this very frequently, upgrade the versions of it, things like that. So essentially, generally prefer to have one queue all over the org, generally. So we would be using whatever the queue that is there. Let's say PubSub can also handle this throughput. Kafka can also handle this throughput. For our sake, we'll be going with Kafka. I'll tell you why. Because Kafka here, we can also partition your data based on some key. And we might need to partition very high requests coming in. That's why I'm choosing Kafka for now. And and frankly, any queue with horizontal scaling would do this job. And because it's suppose high throughput is low latency, we would prefer this. Cool. Going next. So finally, we came to this conclusion that, okay, you will have a pricing system design. Is this, you have your system, you have a configuration store, you call distance service, you call dynamic pricing, which I'm not come yet. I'll be building that. The interesting part of that later on. You build this system and you finally publish to consumer, and you return your response. So you don't wait for the consumers to consume, you return the response back immediately. Cool. Any doubts on this before we move on to the dynamic part? Any doubts on the static pricing system? You can also put a cache over the configuration store to improve performance. I think one question is that what is the better approach to using a CDC in the database, pushing messages queue, publish queue and stuff? I think both are fine approaches. It basically depends on your domain here. So right now, I am publishing. So some data might not be available because we're not storing anything. We're trying to make this as stateless as possible, the pricing system. That is why we don't have any database to store this data. If you have a database to store it, definitely CDC is also a good approach. And if you need to maintain the CDC itself, the whole pipeline for CDC, that is one thing. But both are actually fine. It is generally, so if you have any custom messages to publish, it is generally preferred to have topic based, like custom publishing. But if you have, let's say, an order management system where in which you are very coupled to the database, all your operations are done and maintained in a state in a database, a CDC is preferred there. Where I think we call that outbox pattern or something. But yeah, that's generally preferred. Cool. Any other questions? Cool. So we have built a pricing system here, pricing service for a static price. Now moving to the interesting part where you have to build for a dynamic price. Cool. So okay. Now
Akshay, there is one question in the question section. Could you check that?
I think I answered this already, the CDC one.
Okay, thanks.
Cool. Yeah. Now moving on to what is that? Now let's see the interesting part where you have to model your dynamic pricing. So dynamic pricing has demand and supply. As I already said, demand, you have to be very careful with this. Like you have to understand demand and supply very carefully because that domain model will be based on this. Demand is nothing but number of pricing requests that come for a user for a unique pair of lat long for every minute in a city in a day. So now let's say as a user, let's say 10 users hit 10 pricing requests. That is what we understood the product requirement. 10 users hit 10 pricing requests in a minute, and that means the demand for that minute is 10. But demand can not be over a minute, it can be over multiple minutes as well. So product has given a requirement that demand is over 5 minutes, which means for every minute of the day, for every minute, you will calculate the number of pricing requests for the last 5 minutes. That is your demand. That is the requirement given to us. And now you can definitely model it directly by saying this 5 minutes, you can calculate the last 5 minutes request and tell you that is the demand, or you can model it in such a way that I will build it like every minute I'll calculate the demand, I will sum it up over 5 minutes to get the demand. Both approaches are fine. We'll be talking about that later as well. Now, what is supply? Supply is nothing but number of drivers available over every minute in a given city. Now, how do you calculate the number of drivers is something that needs to be thought of, which we'll think when that comes. So now, and that also has a time bound. Time bound is 1 minute, and there is a geo bound. That is geo where city is a geo here. So number of drivers available in a city over the last 1 minute. Ideally, in ideal cases, city won't be the geo. It will be much more granular level in companies like Uber or any ride-hailing company, much more granular level to have. Let's say if you're in Bangalore, there'll be like Marathali has some separate demand and supply. Your Indiranagar might have some separate demand and supply, and based on that, price will change. But for the sake of discussion here, I'm just keeping city as the minimum level. Cool. Now moving on, how do you calculate demand? Do we need a separate pricing system or dynamic pricing system altogether, or can you do it in pricing service? So you have two approaches where you store each request that is coming into a pricing database. You fetch the last count, or let's say count unique lat long user from table for time slot between current minute and the last 5 minutes. That is one approach. The second approach is where you listen to the logs of pricing service. Now you already published your queue, right? In our case, you're using Kafka. You published your Kafka. Now Kafka listens to this. There's a service called dynamic pricing, which listens to the log in Kafka and pushes into some demand storage. And so, what is the difference between two approaches? This approach essentially means for every request that comes in, we'll be doing an aggregate query, a unique count star query on your database for the last 5 minutes and returning back the response. What would happen with this approach is a higher latency, but an accurate result. Option two is more of a pre-compute system, where in which you have a dynamic pricing, you have a service listening to it, we'll calculate the demand and supply and keep it somewhere. And whenever you want, you will query the service, it will give you immediately the value back. Cool. Choosing the option. Both are fine. But option one, it's always the answer always it depends. So option one is an easy approach, which gives accurate data, but there's a latency involved. Now you have to do an aggregation query over last 5 minutes. And to frankly to see, there'll be 820,000 RPM requests coming in, and around every record, if it's around 50 bytes also, it would go around I think 16 MB or something. That would be the rough calculation around it. To go through that, it has to go through and figure it out. And you can always make that better with proper indexing and stuff. So that is where, but option one is still a viable approach because there's not enough data. Like there's not much, like going through this much data is still fine. The latency would still be under, let's say, 50 ms. But what if the scale goes into like 10x, 100x and stuff? Doing the aggregation in the database at this point, because you've chosen a Postgres as well, would take a little more time, and that would impact the latency. And you would not want that because dynamic system, already the product told us that for building a dynamic system, if dynamic system is down also, it is fine for us. We need to return back the price immediately, which is why we'd be going with option two, mostly a pre-compute system. And there's one more advantage we get over this is that we are actually building a separate we are actually building a demand and supply system. Now, this system, whatever we store here, can be used by multiple other things, which is another requirement as well in our initial requirement phase. Cool. Now, moving on, what will be the data model of demand? Demand is nothing but number of pricing requests. So I put three data models. One is you can leave the city ID, country ID, date, and time slot. Time slot is nothing but we need to, because we are going to calculate, we are specifying that we will calculate every 1 minute the data and keep. That is the minimum unit of time that we are going to keep. And this has to be clarified in the product. If you want more granularity, you can have it, but generally not required for our use case. So we are telling we will in our demand storage we will keep 1 minute data stored. Now, how do you know it's 1 minute? Basically, with the help of date and time slot. Time slot is nothing but, let's say you divide your total number of minutes in a day, and let's say it starts from 12 o'clock night and early morning 12 o'clock. The first minute would be counted as slot one, the second minute slot two. Similarly, there will be 1440 minutes. Now, as I said, the minimum granularity we'll be fixing will be 1 minute duration in our case. We can always work without granularity, that I can explain probably sometime later, without like to have completely like sliding or dynamic window. But we are keeping it only 1 minute for our case. So now there are two ways to model this now. Now you have time slot, and you can model it as an estimate count, which means you will be storing the total number of count for that last minute, or you can store it as estimate IDs. You can store every request as separate entities, and you can aggregate it in your application layer or in your query layer. So what is the difference between these two? There's a big difference here, because when you start storing estimate count in your storage, it means that your writes are going to be slow. Your writes have to take a row level log. So let's say your row is there with value 1. When you want to update that row with value 2, you have to first fetch the value from row 1 and then update it to 2. Add 1 to it. So which means the summation, it means your write would be slow here. Here, what would happen is your query would have to read all the values and aggregate it and sum it up. So, and in your application, you have to sum it up. So essentially, this gives some latency towards read. So this is little write heavy. Write latency would be high. Read latency would be high here in terms of application. So now, or there is also one way. If we can store all this in memory, wouldn't that be the highest performing thing here? Yes, but probably we need to see if we can store it or not. We can have a simple set data structure where your driver ID comes in, and you can just sum up the set, and summing up in a set is open. So you can sum up the total drivers in the set. That is one approach. So now what we'll do is we'll figure out what data model to use based on our whatever request listing. Storage demand is there. So let's do some calculation. We know that there's 820,000 RPM, and 50 bytes of data would mean there's around 41 MB storage per minute. So you're going to store 41 MB per minute. And now, given we need to store 15 minutes, it means we'll be storing 615 MB. Why do you want to store only 15 minutes? Why not old time? Like let's say one day data. You don't require this essentially because you are going to serve this real time. And if someone wants, let's say 1 day before data, 2 day before data, that can be served by your analytical store, which can be filled slowly. It need not be real time. It can be filled slowly and, have an OLAP database, completely different database model, like a proper data lake where in which the data engineering will be taking care of the complete pipelines to build it and OLAP, this thing. And why not use OLAP for our use case? Because OLAP generally has a very high SLA for read and writes or response time for read and writes. So now generally, so then what would you use? So we don't want to store all the data. Like if you're storing 615 MB data, you can store it in memory, and that should be simple as possible, like 615 data. So now, or we can still store it in database, but not required. Why? Because your in-memory performance would be much higher. So, but in memory means you can't store it as a global variable in your system because that would mean that you'll have to manage fault tolerance. You need to manage disaster recovery and stuff like that. So you would essentially use a cache and a centralized cache. So now in this case, cache storage could be Redis. Why Redis? Because you can use any cache storage, and as long as you can persist data for some time, and we are fine to lose data for a minute. So Redis has the approach where you store your cache data, you store it in memory, you then publish it. You have an append log, AOL logs, and then you flush the data to disk at a specific interval of time. So if during that interval your Redis crashes, the data is lost, which is fine because we have the data till the last flush interval. So generally, if you keep like 5 minutes data is lost, it's still fine for our system because if as we said in the initial requirement, because if dynamic pricing is down, we can still show the static price to the customer. Now, how would you store? Like, how would you store this in Redis? That itself is a data modeling problem. Okay, let's start with your for demand. You will have a drive the key. You'll have set. You can store it in a set. Why set? Because you can have duplicate requests coming in, and you don't need to have application logic for idempotency to handle duplicates. You can handle in the set itself. The Redis can handle that for you. And then so what you do is you store driver IDs in a set. Now what will be a slot? So now how do you store driver IDs? You have what you need to calculate is you need to calculate your demand over last 5 minutes. I can tell that as sum of demand over every minute that is there for every time slot for the last 5 minutes. So if you do that, what we can do, as I said, we can have a set for each time slot. So time slot 1 essentially means 12 to 12 12 to 12 will have, let's say, your demand X, or let's say 10 driver, 10, sorry, this is not driver ID, this is request ID, my bad. So 10 request ID coming in and storing it. Then the demand for slot 2 where there is 10 requests in coming in. And so you sum up for last 5 is you sum up the total count for that set. The cardinality of that set summed up for 5 minutes would give you your total demand for that 5 minutes. And what do you achieve with this is not just for 5 minutes. Let's say if the product wants to increase the calculation of demand time to 15 minutes, you would just have to add all the 15 sets value. So we built a very scalable system and a very scalable to feature system, where in which you can calculate demand for any time that is possible. Now, the one issue is that how will you now remove this demand? So now let's say you keep on creating sets for every slot, you would then Redis would go out of memory because you're storing in memory essentially. So we need to have a scheduler to delete this, whatever is not required before 15 minutes. You need to have a scheduler for that. This is because Redis does not give a TTL over the complete set. So an in-memory scheduler or an external scheduler calling an API would also be fine to delete this data which is older than 15 slots. Cool. Any doubt till demand? The calculation of demand. Cool. I assume all of you understood. Then the next thing is calculating supply now. Now supply is a little tricky because demand, we know that every request comes in. Now what is supply? Now we need to define what is driver availability. Driver availability over an area can only be told by the driver app. The driver app, there should be some mechanism for which the driver app can talk to your system, and this system needs to tell you where the driver is and what time the driver is present in that lat long, latitude and longitude. So how do you do that? You should build a polling based system where in which a driver tells driver app polls or like tells your backend application that I am here, I am alive in this location at this moment of time. So how do you communicate driver app and the backend? you can communicate through two mechanisms. One is obviously polling. Every 10 seconds, you can have a separate thread from the app polling backend, or you can have a WebSocket connection over it's a long running connection. What is WebSocket? Long running connection, which will send in every 10 seconds, let's say, that I am alive data. What is the difference? What would you choose here? I would not like to go more into it because that is a whole system of its own. But generally, the trade-off is polling is resource intensive for the server, and WebSocket, you need to manage those transactions, or sorry, you need to manage those connections. If there's a lot of very high scale running, managing the connection would take time, like would be a little cumbersome. Which is why here I would go with polling, and WebSocket is also fine, or some other long running protocol also, MQTT or whatever it is. Now, how would the data modeling look like? Very similar to your request that comes in for demand. This would also have driver ping count. It could be, you can store it as a count, you can store as the ID with the time slot, very similar to what we calculated for demand. Or we can store, as we said, for demand in memory also, if we can try it. So now we'll go to that. So now, yeah. Now let's go to the part where let's figure out what data model to use and what storage to use for storing the supply. So there are 4 million drivers in the requirement set. This is why whether your requirement to understand scale is very important to choose this components. There are 4 million drivers. They send ping every 10 seconds. So now there are 6 pings every minute, which means now 6 into 4, 24 million pings every minute coming in. So, and if every ping has 50 bytes of data, very rough estimate, 50 bytes of data, that would lead to a total of 1.2 GB of data required per minute. And storing 1.2 GB just for 15 minutes would have, you need 18 GB of data. Can this be handled by a single Redis node? Obviously, you can handle it. You can handle it. You can have a 32 GB RAM machine and use that as single node Redis because we are only going to store 15 MB of data. What if in future we want to store 30 MB data? We would require 36 GB of data to be stored in memory, which means you'll have to upgrade the machine. And vertical scaling after a point of time is very costly compared to horizontal scaling. And so, what is the solution here? There are 3 solutions which I'll explain to you. And one is the Redis solution. The Redis solution is where you'll have a multi-clustered mode of Redis, where you have multiple nodes on Redis, and this Redis and each Redis, let's say there are 5 nodes, each one, let's say if it's 32 GB also, each one would only have to store 6 GB of data. And definitely there would be issues with this also, but how will you structure the data in this case? So thing is, similar to supply, we can have a set, we can add slots and store it. But there's one issue in this data model is that my driver 1, let's say driver 1 is pinging for slot 1. Driver 1 can also ping for slot 2. When you add for the last 5 minutes, it will be duplication of data coming in. That is why we'll have to model in such a way that duplicates cannot be found when you add this data. And how would you solve this problem? You can solve it in a very resource intensive way. It's like having, we need here last 15 minutes data. So you can have 15 different sets. So all the 15 different sets will be, you'll have slots 15 to 14 minute, 15 to 13 minute, 15 to 12 minute, and 15 to 1 minute. Slots like this. Now for every minute change, you'll have to recreate slots or rename your slots. And luckily, renaming of slots in Redis takes around 1 complexity. So that's still a good approach. So now you have 15 slots. Concurrently, you can add this driver to every slot whenever a ping comes in. And that would still perform better than database because Redis update would take around 5 microseconds, 10 microseconds. And for 15, it's concurrently anyway handling it. So even if that would still perform better than a database, but what essentially a driver ping would come in, you would update all the 15 sets concurrently. If there is a new minute event, probably you can handle it through storing a key value. You would have to rename all the sets. And that is still fine. It is still a good viable approach for us. What is the second approach? Second approach is database. Store all the values as audit logs, meaning all the pings that come in, just dump into the database with whatever time slot that is given. And now, how would you fetch the data? You would have to fetch the data for the last, 15 minutes for the demand. You'll query for the last 15 minutes. You will have to fetch 1.2 GB of data. But this is a very huge amount of time would be required for aggregation here. Now, but is there something better we can do? Yes, we can shard our system or the database with the city ID because your demand, as I said, is over a city, and that geo will help you shard this data. So now let's say you shard your data over city IDs or multiple city IDs, or with a where query here also with city ID would give you like divide this by 50, 1.2 GB by 50, 50. That is still a little performance issue, but we can still choose databases appropriately necessary for this. So out of these two, we can still prefer Redis as starting point, And once any performance impact, the scale increases because 4 million drivers to 8 million drivers would take a long amount of time. And that means adding countries, and it won't be a direct scale coming in because drivers are fixed at the moment. That's why you can still go with the Redis approach over DP approach. But there is one more approach that I would like to discuss, which is mostly around. Sorry, there's one question here. How will we take into account the latency? So the latency, if you're talking about this 15 sets latency, it is basically, let's say you are not going to query it one by one sequentially. You're going to take it over 15 sets, and Redis will handle all the concurrency part for you. It is single threaded. You can have multi-threaded mode also. But let's say 50 microsecond, right? It will be 50 microsecond, sorry, 5 microsecond per request. Even if you take 50, it'll count to 250 microsecond, not even a single millisecond, which will be much performant than database because generally this will also be taking around 1 ms at least. And to find out the exact latency, I would still prefer to load test this whole system with Redis, and not the whole system. At least load test Redis with a custom script and load test database with a custom script, and figure out what time what is the better time, latency in this case. And that would essentially we would go to the better solution to that. Cool. I hope that answers. Otherwise, you can ask another question on that. Cool. That's the third approach. Very interesting approach, and probably so this approach is based on the research paper by Google called MapReduce. So what this means is that you need to essentially do your aggregation. In this database case, you will do your aggregation on your database level, on your query level. You will tell select count star of unique driver IDs over the last 15 minutes, and that means going through 1.2 GB of data. And over this data to be handled by one node might require time. It might take time. So what do you do this? You distribute this data into different nodes and try to calculate it around different nodes and merge it to a single node at the end and count the total number at the end, which will be a much faster approach. So that essentially is, I won't be going deep into how it's implemented. Probably I can share a blog for the same. But yeah, what you do is you have your Kafka, and your Kafka listens to a data pipeline. This data pipeline would have a window. So in our case, let's take a window of 5 minutes. If the demand is for 5 minutes. So what you store is you store data for the last 5 minutes in memory. I mean, in different nodes. This completely abstracted out generally for you. But this, what would you would window the stream, but these window would also ensure high availability of this, which means this would be persisted in files. This would be persisted among multiple nodes. And then there is a map and group by driver, because you need to add per driver. This is an aggregate step where in which you shuffle the data among the nodes, or in whatever process you want to. You shuffle the data, aggregate it there, and then finally store the exact count to store. So instead of storing all these audit logs directly sync one by one to the store, you would count it, aggregate it through this MapReduce function, and store it into store a single count. So the fetch would be very simple. Fetch from a last minute, and that will give you exact value from here. No aggregation in the database required because we already implemented something called a distributed computing here to aggregate and store it. This is also one viable approach. What would we choose? Starting off, we can obviously go with Redis. If there are performance issues, we can still go with database and figure out if the same performance will be there. If not, finally, we can go with this approach where you have a aggregation pipeline running, where and this aggregation pipeline can be implemented through, let's say, Apache Spark, GCP Dataflow, whatever data engineering use case that is there. Now, one issue with the Redis approach also I would like to tell is that there is a limit on number of sets that can be made, a number of elements in a set. So in in Redis at least, I think it's 2 power 32, which is 4 billion keys. 4 billion keys only can be kept in a set. So now when your driver exponentially increases, rare case, but still possible case, exponentially increases and starts throwing pings, you might not go with the set approach, and the performance might be impacted there, even after, let's say, 1 billion as well. You might need to move to an approach where there is a data pipeline or a proper database specifically used for good aggregation tools. Yep. And finally, let's wire it all together. What you do is you'll have a request, you'll have an API gateway, you'll have load balancer calling pricing service for static pricing, calling configuration store with the cache, calling distance service. It fetches. This is and there's also 2 lines here. One is to publish the event. Dynamic pricing will pre-compute the dynamic and demand and supply. When a request comes, it will call dynamic pricing service to fetch the dynamic calculator and return back your request. And that's all for the problem statement. Cool. Hope it was interesting. If you have any other questions, do ask me now. I think we finished on time.
Yeah, it went over for an hour. Awesome. Folks who are listening to us live, if you have any questions, please drop them in the Q&A section. In the meantime, Candy, if you could check if there are any questions on LinkedIn.
I think around the slides part, I think I'll write a blog on this very soon. Like I was anyway writing on it, so I'll share the blog with you completely. Because slides there are missing information as well, like the driver pings and stuff. How do you build that system as well? I'll completely write it in a blog and send it to you. I'll send it to probably Rebase,
And we will
Recro, and they can
also
share
be
it.
right, and we will also be sharing the recording of this session in the community. So if you are not a part of our Discord server yet, you can join the server. Not only you would be able to get other resources like this, and you would be able to connect with other mentors from good product-based companies. You will also get that along with this resource. So yeah, I think you already have the link. Canada from my team has posted the Discord server link in the chat. You can join the server. Let me quickly have a look at the question.
Sure, I knew this was a little fast. The question went like in the presentation went a little fast, but do go through the presentation and see the recording of the video again to understand a little more in deep all this stuff. Because it's better if you guys actually can now you have an idea of what components to use and how I am thinking of it. Probably you can write yours, like you can think of the problem statement, see the requirement again, and think of how you would build the system and compare it with this, and then you can see the problems faced by my system and compare the problems faced by your system.
Akshay, there's one question on LinkedIn asked by Sayed. I think the question was asked when you were talking about the demand supply,
Mhm.
calculating what would be the demand and supply. So you talked about the 5 minutes concept there, right? So the
Mhm.
question was, what should be the multiple, like minutes or seconds, when we are saying last 5 minutes, and what other factors should we consider while deciding that multiple?
No, so as I said, we will. So when you're building a product, when you're building stuff like, let's say, I am at 12:55 time, and now you would want last 5 minutes. You can obviously check from 12:55 to last 5 minutes, which is 12:45. How many requests are there? And but I think that approach would require more effort, and I mean more effort in the sense more cost and more components to be designed for that. But more importantly, what I have assumed here is for a use case like this, we can fix our window to 1 minute. So every minute you can count and store this value. I think because that was explained earlier, it came out later. That should be answered in the slides itself later on. But every minute we fix a value, we try to calculate the value and store it. So the minimum unit of time we are storing the value is every 1 minute, and every 1 minute you're storing this value. And at the end of the day, you can aggregate and fetch the data over 1 minute time. And it should be calculated over 1 minute is what I think in this case. But you can obviously, if the product says no, I need every 15 seconds because I need last 15 seconds data, sure, you can aggregate it over last 15 seconds. But just to point out that in this case, because driver polling is over 10 minutes, sorry, your driver polling is every 10 seconds, you need to think of that as well when you decide the time to store this.
Awesome. Akshay, there's a question in the Q&A. It says, how do I become like you? I'm a very junior engineer and want to become like you. You want to answer that? Any tips that you have to, any tips that you have to give to those who are very early on in their career and want to grow?
Oh, sure, sure. I think early on in your career, the first 2 years, probably you should concentrate on your programming skills, which means you have to learn, let's say, implement like code as much as possible to the limit where you don't like design patterns and all. You can't learn design patterns. You code and figure out issues and question your code, which in turn evolves into some design patterns, and that's how your code evolves. So first 1 year, probably you concentrate only on code and a little breadth where you understand. Like what is the database, how does the database not internally work, little high level you understand, and then you move on. Then after 1 year time, you'd have an understanding of how you can write an API. You can write an API which calls a database, which calls a network call, and which gives the result. Second year, probably you can concentrate on understanding the domain. Now when you call a database, you need to know what domain model you have to create for the database. So you need to work more on the domain modeling in there. and post domain modeling, then is the time where okay, you can actually build a product by yourself. Now it's mostly a decision on what database to choose, what language to choose, what is a communication protocols to choose, things like that. So now for that, you need to understand little internals of the database and stuff. And that's when you go internally into different technologies and how a database works. Like let's say if you're storing into files, does database directly store into files? No, they have, let's say, a wrapper over it. And I won't go deep into it. Let's say how does TCP work? Do a little bit of socket programming, and then move into one basically. Let's say database means, let's say, go into internals of database. How do you make a database? What are different kinds of database available? And then move into one in depth. And then after you complete that and you're satisfied with that, move into another depth. And that's the only way you can improve.
Awesome. Um, so I don't see any further questions. Um, folks who I also rolled out a poll, and looks like people enjoyed it and learned something. So thank you so much for that. And folks, those who want to stay updated with such webinars, you can simply check out recruit.io/talks. You can see all the upcoming webinars over there. The next webinar which is happening is on React 18 concurrent rendering deep dive. If you are interested for that, you can register for it. I have shared the link in the chat. So awesome. I think, Akshay, we can stop the screen sharing now.
Cool.
Yeah. Awesome. So I think that brings us to the end of our wonderful discussion on high level design. A lot of questions that came from you, and I hope that it was helpful. Everything that we have discussed, it might have been super fast, but since the topic was topic needed us to cover this length so that it could be valuable. But I hope you liked it. Thank you so much, Akshay, once again for joining us and taking out the time and explaining everything in so much depth. So really appreciate and value your time here. And I look forward to having you for another webinar super soon.
Sure, sure. Thanks for having me.
Awesome. So, folks, that's all for today. Next week, another webinar next Saturday. So, join us there as well. And those who are still not a part of our Discord server, the link will be shared to you. We will be also dropping an email, which will also have the link to join the server. You can join us on that on Discord server, and we look forward to having you there. And I'm sure you'll have a great learning experience with fellow developers and other mentors as well. So on that note, thank you so very much. Enjoy your weekend. Thank you so much, Akshay, again for your time. Have a good evening.